Hello, everyone. Thank you for joining us for today's webinar. My name is Kaylin Shores, and I'll be moderating today's presentation on easier full device modeling for EMC and ESD. Before we start the presentation, let's review the user interface. On the top of your screen, you will see a bar with 4 options for you to click. To ask questions, please click and open the Show Conversation option. This will show the meeting chat, and this is where you may ask any questions you have during the presentation. At any time during the presentation, you may submit your question. Your question will be placed in the queue and will be addressed at the end of the presentation. Any questions left unanswered will be responded to via email. Now on to today's speaker. Tim McDonald is president and co-owner of EMA, where he has implemented new system modeling approaches to simulate the interaction of systems and their electronics with electromagnetic environments in a shorter time, with more accuracy, and at a lower cost. Tim previously led consulting engagements for NASA and DoD major primes pertaining to specialty engineering of critical systems and of development of novel solutions to electromagnetic compatibility problems. Without further delay, I'll pass it off to Tim to get us started.
Thank you very much, Kaylin. When I started my career in EMC, the way that we certified devices was a prototype device was developed. We took that prototype device to a chamber and analyzed it, tested it for EMC compatibility. The problem with this approach is today the cost and the time expense to have a prototype is considered very prohibitive. Almost nobody wants to run prototypes anymore. The reasons are obvious. If you fail EMC at the prototype phase, it tends to be close to production. And as you're scaling up, it's more costly if you find problems at that time. Also, our product development cycle using digital engineering techniques means that the time allowed for development is reduced, and having extensive time periods where we have prototype, change the design, prototype, that doesn't happen anymore. Also, at the beginning of my career, electromagnetic simulation existed and the solvers were very advanced. People have been using electromagnetic simulation for decades and can do very accurate models of electromagnetic phenomena. However, at the beginning of my career, it was not considered possible or really practical to do an entire device simulation. It was just that there were too many things happening in the device. There were multiple boards. There was the fact that the mechanical CAD was not necessarily compatible with the electromagnetic simulator without an extensive amount of manual redesign, manual cleaning of the model to get it ready for simulation. So while theoretically a full device could be simulated, it was not typically done outside of research and development projects. However, the technology has changed. So that's what I'm here to talk about. The ability to use simulation for entire device modeling and the ability to have these digital simulations replace some of those early prototype phases. I'm going to talk about a couple of products. They're ANSYS EMA3D Cable and ANSYS EMA3D Charge. EMA is a technology partner of ANSYS. We supply these products to ANSYS, and the products are commercially available through ANSYS. Separately, EMA has a team of consultants that works on design, troubleshooting, and validation of equipment to electromagnetic compatibility requirements. So there are services to help you when you fail a unit or you want to get involved in full device simulation, and there's products that you can buy. The simulation products are from ANSYS. The services typically are from EMA. So the first product and the first workflow I'm going to talk about is EMA3D Cable. It is a unit level electromagnetic modeling solution for entire devices or entire platforms. And when I say platform, that could be a car, that could be an aircraft. Essentially, we're looking at things from unit enclosures on up. So this is what the product looks like. It is an all-in-one product, meaning that you can import the CAD, you can prepare your simulation, You can run your simulation. You can analyze your results compared to EMC limits and normatives. So let's talk a little bit about some new capabilities that have been added recently. Not only can we do the electromagnetic simulation of the structures and the cables, we can also now do circuit simulation. Where does EMA3D cable fit with the other ANSYS electromagnetic products? ANSYS SI Wave is a tool for PCBs and packages. It's extremely efficient, very fast. By combining the ECAD, the electronic CAD for the PCB, with details of what the circuit and the components look like in a circuit model, engineers can quickly build up digital representations of their PCBs and packages and simulate them for signal integrity, power integrity, but also they can predict EMI, EMC. Now, we know that EMC at the board level is incredibly important. That's a key part of the workflow. But there's also box level, device level, as well as cables impact on the EMC standards. So EMA3D cable, even though cable is in the name, it's really about more than cables. It's about extending that EM simulation to the entire device, including the enclosure, multiple boards, interconnecting cables. All of those aspects can be included. So the key goal for EMA3D cable is the workflow. So what I had said in the introduction about how it was considered theoretically possible, but impractical to do a full device simulation, the goal of EMA3D cable is to take that impracticality and make it be something that can be done in a reasonable period of time. Another thing to point out is EMA3D cable is within the ANSYS Discovery product. It's basically a CAD front end that can import arbitrary mechanical CAD files. The workflow in EMA3D cable is built around CAD. So ANSYS Discovery under the hood is the enabling technology for that. ANSYS HFSS is another product for antennas, components, interconnects. EMA3D cable can pull in fields from HFSS. Finally, EMA3D Charge, it is a tool for charging and discharging. We'll be talking about the ESD environment toward the end of this presentation, so that's where we'll introduce that product. Okay, let's get into a very important EMC environment, that's intra-system operability. So how can the device operate in the presence of the device's own antennas? The last thing we would want is to degrade the performance or desensitize the performance of our electronics RF systems just from their normal operations. So this is a huge concern. So to introduce the capabilities to full device modeling, let's start with the full device. So the device most of us hold near and dear to our hearts is our cell phone. This is a good example of an electronic device. So this is a non-proprietary but extremely complex model of a phone. It includes structures for the screen, the case, the PCBs, details for the cables themselves. The way EMA3D represents cables is unique. The path of the cable is tracked in 3D, but what is inside that cable is defined in 2D. So that reduced dimensionality, along with a modification of transmission line theory, lets us specify things like shields, foils, braids, conductors, branches, all of that in 2D world, and cast that onto the path of the cable in 3D. And we can co-solve those two solvers simultaneously, time step by time step. So for users, that's a huge time saver. If I had to create the twisting of cables, if I had to create the complex path, the tiny sub-millimeter braids of the weaved cable shields, that would be incredibly impractical, to say the least. So what this product does is by abstracting the definition of the cables in this way, that can save us many hours, days, maybe months of time preparing and running the simulations. The other thing that's key is our ability to have a voxel mesh. So we'll see what that looks like in a moment. So let's take a look at some of these live demos. So again, this is what the cable itself looks like, and we can take a look at the individual conductors. And it's based on a hierarchy. We can group conductors together so that we can set the twisting pitch. We can group conductors together into a shield. We can specify details of braid and foil shielding effectiveness or transfer impedance parameters. And that allows us to very quickly specify something that is extremely tiny, but get it specified very quickly. And with the tool, we have the ability to look at not just the external parts of the case, but we can also look at the internal PCBs, the traces, the other parts that are inside of the phone itself, as well as very critically, in this particular case, we want to study that Wi-Fi antenna. And so just to point out what I mean by the voxel mesh, that means we're going to be gridding everything up, and we will be solving across something that creates tiny, tiny voxels. So voxels, think like Minecraft. They're tiny boxes. And so by using those tiny boxes, we can dramatically reduce the time it takes to build and analyze our models. So we take a look at the Wi-Fi antenna. What we want to answer in this particular example is, what is the coupling between this antenna and the power cable, the USB cable that I use on this phone? So we're going to use something called a scattering parameter, or an S12, to calculate the frequency dependent coupling between the Wi-Fi antenna port and a port that's assigned on the end of the cable. And that S12 is going to be expressed in decibels or dB. So first, we run the antenna by itself in a simulation. And so we are calculating the S11, and that is telling us the frequencies that the antenna operates. So just as we would expect, we see that the antenna is operating at 2.4 and 5 gigahertz in this particular example. And then this picture is showing a slice through the center of the geometry, and we're capturing the E field as a function of time, and the intensity is represented by color on this plot, showing the coupling happening. And then in the plot on the right, we can see the S parameter matrix with the units of dB. So we can see at a peak, we're approximately about 35 minus 35 dB coupling from the antenna to the cable. So at each frequency, we'll be able to determine what is going to couple from one to the other. And by using that with other products, such as ANSYS EMIT, we can make estimates about whether or not we're going to have issues with the performance of that particular RF system, the Wi-Fi system on this device. So we've taken something that, as I said in the beginning of my career, if someone said we would like to determine this coupling, really our only choice would be to build the phone and make this coupling measurement. It would have been considered really a multi-month, maybe multi-year research project to model an entire phone. But today, that's no longer the case. Okay, let's talk about other important coupling cases in intra-system EMC. In this case, what our concern is that we have a cable, connector, and pins from an HDMI cable. And the concern is where those pins terminate on the device, how does that couple through fields and waves to a nearby PCB net? So in this case, we're going to take advantage of EMA3D Cable's ability to abstract details of the cable shield. So the HDMI cable includes both foil shields, extremely thin foil, and braided shields. And those braided shields have tiny, tiny filaments of metal, tiny wires that make up that braid. And those wires are smaller than a millimeter. to be able to 3D resolve that braid would be extremely computationally expensive, but more so just the man hours to try to build that braid in 3D. It's painful. It's not a fun process. What we want to accomplish is to reduce the amount of analyst effort to prepare these models. So that's where EMA3D cable comes in. You can see the size of the grid. We're using extremely small voxels, which allow us to capture the details of both the nearby PCB as well as the connector with very high fidelity. And in the time domain, we specified the signal on HDMI. On one end of the HDMI, you can see on the other end, we're still seeing essentially the bits come through. So we can take a look at the animation. And you can see in this animation, we're able to see how the pins themselves are coupling to the PCB traces. And then we can calculate the voltage versus frequency and voltage versus time in each of those PCB nets, which is our quantity of interest. Okay, let's talk about using other tools with EMA3D cable. EMA3D cable can very easily pull in near fields analyzed with other tools like ANSYS SI-Wave or ANSYS HFSS. Or if users like, they can perform near field scans. SI-Wave is out of scope mostly for the discussion today, but just to give a very brief summary, it's a dedicated PCB and package electromagnetic simulation tool. It can perform signal integrity analysis, but for today, we're going to be focusing on how it can be used to estimate EMI, or more specifically, we're going to put operational signals on the board on each trace, and we're going to see the near fields that are created. And those near fields are going to be used in EMA3D. So let's take a look at the geometry in SI-Wave. This particular board has a processor in the center. On the left, a couple of DDR memory chips. In all, it has 35 addressable nets. So there's two steps to this simulation at SI-Wave. We pull in the ECAD and we're able to calculate the SYZ parameter matrix. Then we can push those matrices to the electronics desktop circuit solver to excite each net. And so the net excitations, they may be clock signals, they may be representation of bits, they may be digital noise representations. Once we've got those time domain signals from circuits, we push them back onto the SI-Wave traces. And then with the SI-Wave solver, we calculate the near field very, very close to the board on a grid all around the board. So this is an example of what that near field simulation looks like. At one frequency, you can see where the hot spots are on this particular board, and they're between the processor and the nearby DDR memory chip. We can measure the fields as a function of frequency. We step through frequencies. And then let's show how easy the fields are to import. So we just select the exported file from SI-Wave. We give that a second or two to process. And then once it completes, you physically see the 3D board show up in EMA3D cable. So the next step is to just translate and rotate that board into the correct position inside the enclosure. Let's talk a little bit about this enclosure. This is not a clean, nice enclosure created natively in EMA3D cable. This is mechanical CAD. So this was designed in order to build this enclosure. It was not designed with analysis in mind. And that's really what EMA3D was designed to work with, is the mechanical CAD. So EMA3D, because it's pulling in mechanical CAD, it's pulling in ECAD, it's not requiring analysts to start from scratch and build their own representation natively in EMA3D. It's all about just straight up using that CAD as is. So let's take a look at what that looks like. We've seen where the board is imported. Next, we can define our cables, we can define our gaps, we can define our seams. The way that we represent seams and gaps is very interesting. So if you have an interface at the lid of your enclosure. It may be extremely small. In fact, the mechanical CAD may imply there's no gap at all. We know that's not true. Whenever we have a mechanical interface, there's always a manufacturing tolerance. So unless you've put a gasket in an enclosure, you're always going to have a gap between interfaces. But those gaps might be tiny. They might be micron size. However, they could be very important for EMI/EMC purposes. What do we do? Do we want to make our mesh try to resolve something that's micron size? EMA3D cable gives us some options. With a single line, we click a line, we can define to that line a specified gap width, or we can define a seam impedance. And that gives us a way to characterize a seam through intrinsic properties and have them applied with a single click. That means that we can keep a coarser mesh, keep our model running faster, and still get accurate results. So this is what the voxel style grid looks like. Again, all of this is unclean geometry. If you try to just import and hit mesh with mechanical geometry and other tools, you may be in for a bad time. But EMA3D cable is all about working directly with the mechanical CAD drawings. So let's take a look at this. So you can see the SI wave board is driving the emissions in the lower left portion of the enclosure. And then fields escape the enclosure through the seam that we defined on the enclosure. And then we can measure or characterize the radiated emissions some distance away in terms of E field or H field magnitude, voltage, vertical or horizontal. So EMA3D with one click does the post-processing for us. So we can see the field statistics at any location in space or any volume in space, and the software will tell us the E field versus frequency. So this can be an incredibly large time saver. You don't have to use a third-party tool like Python or MATLAB. Natively in the tool, you can see your fields and compare them to your EMC limits. Now, we can also combine multiple sources. So as we all know, EMC in devices is more than just one cable on one board. So let's talk about combining multiple sources into one. In this case, let's look at this device. We're going to define a seam again. The red line defines the seam impedance with one click. You can see the orange square in the center of the phone is another SI wave field import. And on the right, we're specifying the cable cross section using the 2D definition. We've got 2 layers of shielding. We've got multiple conductors. All of that can be added with our existing cable library. With just a few seconds, you can specify all of that. This is what the PCB looks like in SI wave. Again, we drop it in, translate it, rotate it to the right location in EMA3D. And then we're ready to roll. You can see the fields from SI wave fill up the enclosure. They escape the enclosure through the aperture that we define through seam impedance. You can see the fields created on the cable. They're going through those 2 layers of shielding. And then at the observation point, we see the combination of fields from multiple sources. So this is showing how we can use EMA3D cable and have multiple sources of fields and have them combined to create a simulation of an important EMC quantity. Okay, let's talk about radiated emissions on devices. They're just a little bit bigger. These days, the biggest electronic device many of us have is a vehicle. Vehicles are becoming a storehouse for electronics. The infotainment system is rivaling what you would have in terms of consumer devices. On top of that, we have electrification. So we have new types of sources. We have new aggressors in an EMC type of thinking. Separately from that, we have more autonomy in vehicles, meaning I have radar telling me if there's someone in the lane beside me. And cars are starting to make safety critical decisions based on those sensors. Whenever part of a vehicle becomes safety critical, now it's got to pass EMI EMC, not just by choice, but by regulation. Most governments have regulations for safety critical parts of vehicles. So we don't have a choice. If we don't pass our EMC, our vehicles cannot be sold when they come off the line. So let's talk about this particular case. We've got a high voltage system. We've got a motor attached to this vehicle. We have got our DC-DC converter to step down to create our 12 voltage system for the vehicle itself. Now, EMA3D cable can import the description of cables from common database software like Zuken E3 series or other cable database tools. We can import them directly. Once we've imported them, we can see the 3D distribution of the cables. They can be built by hand, but they can also be imported if they exist in a database. So this car is CAD derived. This is mechanical CAD. Of course, this example is missing critical things. It's missing the dashboard, it's missing the seats. But in terms of the drive system, it is somewhat complete. You can see in green the cables themselves, and we can also hover over and we can see the cross section. There's our low voltage system where we have data and power cables co-bundled together. And they're the ones that we can consider, well, all of the cables actually, we can put sources on those cables and drive them with a voltage. So let's take a look. First, let's look at the mesh. Again, our very forgiving voxel style mesh gives us the ability to crank through the mechanical CAD geometry in an extremely short period of time. And that lets us worry more about our electromagnetic simulation. We don't have to spend months preparing the geometry for simulation. Now let's look at how we define our sources. You can see every cable has a source. Built into the tool, we've got the ability to create standard waveforms. In this case, we've got pulses with a rise and a fall time. On top of that, we've got the ability to import arbitrary ASCII sources as well. Okay, let's look at the results. We're seeing the radiated emissions. This is E field on a slice through the vehicle. So the operation of those circuits near the drivetrain are creating fields. The shields on those cables are attenuating those fields somewhat. Then the structures of the vehicle affect the distribution of fields. And then some distance away, 5 meters, your observation point, you can collect the fields in volts per meter. From a different angle, same thing. You can see, obviously, the fields are coming from the cables. They're red hot. And as we get further away from the cables, the field intensity drops off. And what we're really interested in is probing the fields in terms of volts per meter some distance away from the vehicle. Okay, we've talked about emissions. Let's talk about immunity. In this case, it's an inverse of the same problem. In this case, our source is off the platform, and we are attempting to determine the volt or current induced on the ends of the cables. So we're using the exact same geometry, but now we have an EMC antenna outside of the vehicle. So we can see that propagation of that plane wave as it comes across the vehicle. And from another angle, we can see the fields induced inside the vehicle. And then we can calculate the voltage versus time, the voltage versus frequency in the termination of all of the cables. So let's take a quick look at how we would go about doing that. So we can select one of the cables. We can select a termination. We'll select not the shield, but the interior conductor. And at this point, we can add an arbitrary circuit. So I can import from a file a component. So I can go on the web to the website of that component manufacturer, in this case for these TVS diodes, I can download their component file, SPICE, IBIS style component files, and I can import them in one step. And I can add that protection, that diode protection to my circuit, and I can rerun my simulation, see how the diode helped or didn't help my EMC performance. So for immunity, having the circuit can be very helpful. Okay, we're going to switch gears a little bit. We're going to talk about another very important EMC environment, electrostatic discharge, or as we're going to call it today, ESD. ESD is a required environment. So really, any electronic device, at least for quality, but perhaps by regulation, you have to pass ESD testing. Everyone knows the ubiquitous ESD guns that are used for testing. It's something that's reasonably straightforward to test, but how do you test it if you don't have a prototype to test? And the physics of an ESD non-contact discharge are hard because we're breaking down air. So we all know what it's like to have an ESD event. So you sit down in your car, we've all had that experience. We've probably all had that vehicle that every time you get in that car, you get a shock. Well, when you touch the infotainment screen and you shock it, the key is we don't want to have a loss of cruise control. We don't want to lose our safety critical functions or even non-safety critical. We don't want the air conditioning, or we don't want to burn out a component because we shocked the infotainment screen when we sat down. So let's talk about an interesting tool. This is a new product. It's called EMA3D Charge, available from ANSYS's ANSYS EMA3D Charge. It is a modeling solution for ESD. It is very unique. It is solving the electromagnetic equations. It's also solving the fluid flow equations, conserving momentum, energy, and particle number. It's solving a nonlinear air chemistry equation, meaning when the electric field is high enough, neutral gas particles will ionize into ions and electrons. When the electric field is low, those ions and electrons will recombine. All three being solved together on the same voxel grid that I showed you before. So the only change in the user interface is I'm going to specify a box of air that can go nonlinear, and we allow those fluid flow equations to be solved on that box. The user only needs to specify where the box is, the pressure, and humidity of the air. Everything else is set up just as easily as I described before. This means that we can use EMA3D Charge to assess the effects of ESD on our circuits. So we all probably know the ESD gun test. So that's what we're attempting to model. Just to prove how close we can get to this prediction, we're going to start with an ESD gun. So we acquired an ESD gun, created a target for testing, and attached it to an oscilloscope. For comparison, we made an EMA3D Charge model of that ESD gun, including the ground strap, which is an important part of an ESD gun. Don't use the ESD gun unless you've properly attached your ground strap. Next step, this is hard to see in that picture, but the tip of the gun and in simulation and test, it's non-contact. So there's an air gap of a few millimeters between the gun tip and the target. That's really the key point because we're going to create an arc in air. So if we take a look at that, you can see that if you look very close right here, that there is a gap to the ground plane. And if we look at the current versus time, you can see very good correlation between experiment and test. So this is really the first time the engineers have been able to assess ESD using a simple simulation tool. Maybe you could create a multi-physics solution by hacking several things together, but it's never something you would want as part of your normal product development process. We can adjust parameters like the gap width. We can adjust the humidity. You can go from Colorado, where we live, to Florida, and you can see how the curve changes. And there's big impacts. This is not a trivial thing to simulate. Or to understand how this couples to your product. You can see the huge spike at a 5 millimeter distance. At 6 millimeters, that spike is gone. It is not that easy to control this experimentally. So you end up with a very wide variation in what these arcs are like that can affect pass fail your product. It's nightmarish to have to deal with this without a way to simulate this process, because it cannot be controlled. That's what we want. We want predictability. We want control. This is an aspect in the past we couldn't predict. Now we can. So let's show how we use this. So in this case, we're looking at this Arduino style board, and let's see how that is modeled in EMA3D. In this case, we've got the Arduino board, we've got the ESD gun model, and all of this, again, it's mechanical CAD, it's ECAD for the board itself. And then we can show this simulation. So keep your eye on the left, on the tip of the gun. On the right, unfortunately, there's multiple things to watch, but I suggest watching the ESD gun tip first. We're going to keep ramping it up, and there it goes. We've got an arc. We're arcing to this USB housing. And now we can look on the right. You can see simultaneously we're inducing currents and voltages, but visualizing current right now on one of the traces of the Arduino board that's not necessarily in the direct path of conductivity. So we can see coupling from fields and waves. We can see direct coupling. You couldn't dream of modeling this in a pure circuit model, and certainly to capture all the physics, this would be hard without this tool. Now it's possible. There's other aspects that people use EMA3D Charge to model. For example, you can have arcing within PCBs. This is an arc in air where the trace distance is just too small. And if you look very closely at the center, close to where the mouse is, you can see in red, we're actually arcing across from trace to trace. Okay, what about secondary arcs? So this is based on a real discussion we had, a real problem, not on this same vehicle. In this case, there was an ESD gun, a required test to the door handle. There was a suspicion, there was a failure observed far away from the handle. There was a suspicion maybe that there was a secondary arc. There is a cable from the door handle to a device inside the vehicle, and there's a shield on the cable. So they were essentially equipotential from the door handle to this device. So the question is, did we make an arc somewhere else? Of course, we made an arc at the handle because we hit it with an ESD gun, but this is a troubleshooting nightmare for the EMC engineer because you're hitting the door handle and you're getting an arc somewhere else. Let's see what happened. So first, let's do this with a small pulse. In the real world, in this simulation, nothing happens. Then we crank up the pulse. So you can see where it is. This is the zoomed in view. Keep watching it. There's 500 frames. We'll eventually see it. We build up the current, and eventually air starts to go nonlinear in the vicinity, and then bang, we've got an arc right there. We've got two arcs. So when we crank up our ESD discharge to the door handle, we observe an arc very far away from the door handle. Because we're solving full wave Maxwell's equations, we're solving the fluid flow equations and nonlinear air chemistry equations everywhere, we can find those secondary arcs. So this is just one example, but there are many, many more. Imagine the distribution of charge in touch screens, charged objects nearby, charge buildup everywhere else. All of your quasi-electrostatic nightmares, this is the tool you're going to want to assess this because it's so easy to use. And again, like I said, we're solving the fields and waves everywhere. So you can see how when we have a discharge in one location, we can see how that's creating currents everywhere in the vehicle, everywhere in space if we want to do so. These are definitely runs that are run on a workstation or small cluster, but they're reasonably computationally efficient. So these are things that can be run overnight. You can see the results in the morning. All right. So we've gone through some fun examples. We've talked about how EMC has changed over the course of my career. Likely it has changed in yours. We have tremendous pressure now to get away from prototyping. We want to start ramping up production, and we just want to do EMC on our first few production units. Problem is, EMC failure of a late stage prototype or production unit is incredibly expensive, problematic to fix. When I started my career, you couldn't do full device simulation. That wasn't a thing. That was a research thing. That was a dream, but it wasn't really done routinely. That's changed. And the technology to do that is right here. EMA3D Cable, EMA3D Charge. These products are available from ANSYS. I encourage anyone who's interested in learning more about them, getting a demo, reach out to ANSYS. I'd start on the product pages, ansys.com/products/electronics, and then /ANSYS-EMA3D-cable, or the same ANSYS-EMA3D-charge. Get on there, get access to these tools if you'd like to see them. Okay, what if you're a product designer? You don't have time to go there. EMA has services. We can help you out. Give us a call. We can do troubleshooting. Did your device just fail last week, this week? Do you need help? Do you need an EMC expert? They're not exactly easy to find and recruit and hire right now. We've had a lot of customers in trouble. So what we can do is we can help use experience combined with simulation analysis to troubleshoot your problem. And it's not a one-off solution. We're going to help you solve the problem that you're having today, but we are also going to set you up with a workflow so that it doesn't happen again. So there's 3 different ways that you can engage our services team. Could be something simple, a single board, single enclosure, single cable, or some simple combination where we're troubleshooting a problem. We have a suspicion of where the problem is, and we just want to know, if we make this change, is this going to mean that we're going to pass the next time around? So we're going to look at your failed test results. We're going to look at your device. We're going to run some simulation to help prove that those peaks are coming from where we think they're coming from. We will give you that simulation, and that will help you solve your problem, the results of that consulting, but you will also have that simulation approach so that you can use it in the design phase next time you come around. So, fix the emergency now, but let's be smarter for the next time around during the design phase. That's number 1. Number 2, what if you got a full design? You really need to make sure that you're de-risking this design, or you failed and it's in full, we don't know where it came from. We need to characterize the full device. In that case, as the point of this whole presentation, entire device level simulation is now possible. This is a medium-sized project. You can get your mechanical CAD, your cable descriptions, your board files to EMA, and we can create a digital model of your entire device. And we can show you how we did it so you can do that in the future. We may combine that with some simple bench testing for some of the black box items that are a little bit hard. There may be components that you just don't know what they're doing. We can use some near field probes. We can probe some cable currents, and we can take some very simple non-chamber benchtop measurements combined with expertise, combined with simulation tools, and we can help you understand more about your product. Okay, there's a third option. This is a heavier project where you would like to eliminate some prototyping. You would like to go into your EMC simulation knowing you're going to pass, but you're a larger manufacturer. You need to prove out this workflow. So in this case, we're going to combine the full device simulation, like the medium offering, with some actual anechoic chamber measurements. And we're going to work with that model to make sure that we have good correlation between experiment and test. And when we're done, we'll have teased out all of the techniques for your specific product family to get that good correlation and give all of that to you. So that can be transformational. That can change your entire company processes. That's a larger services engagement, but it's definitely something that companies are interested in, and they're that's for when they're ready to go fully into a digital approach. So we're happy to help with that. The ways to get information here, of course, our website, EMA3D.com, or you can reach out directly to our VP of Sales, Dan Odom, dan.odom, O-D-U-M, at EMA3D.com. Again, reach out to our services team. So with that, I believe that's the end of our prepared slides. I'm going to go back to Kaylin for any questions.
Thank you, Tim, for that informative webinar. Now let's get to the questions we've received. Reminder to ask questions, please click and open the chat or show conversation option at the top of your team screen. This will show the meeting chat, and this is where you can ask any questions you have. So we'll get right into it. Our first question is, how long does an EMC troubleshooting service engagement take?
Sure. So if you have just failed a test and you need help right away, we can likely help you quickly. So in some cases, we've had troubleshooting engagements when we've been able to get to the bottom of the problem in 10 days, 2 weeks. Um, we want to make sure we get all the way through that. We can help identify the problem, but we want to get through that single board enclosure or cable analysis so that you're left with something besides here's the problem. So usually that engagement will stretch out over the course of a month, but again, we're going to be attacking the problem and trying to elevate that during the first 10 days of that engagement. So that can be very fast, and if you're in trouble, that may be a way to go. If you're looking at a full device with bench testing, those engagements are usually on the order of a couple months. A lot of that time is spent making sure that you can gather up those MCAD, ECAD, cable details, and maybe shipping us a prototype if we're doing some bench testing. The EMI, EMC anechoic chamber lab validation, that's generally a process. So that's going to be 3 months, 4 months process. But again, the goal here is to change how you do EMC going forward. We're going to do validation. We're going to measure the actual unit. We're going to apply what we learned from that measurement to make the simulation better and leave you with something that can maybe change how you're doing your EMC processes going forward.
All right, next question. What information do you need from us for EMC troubleshooting?
Makes sense. So if it is number 2, the medium or the large style, we may ask for a unit itself. If we're doing simulation and not doing benchtop or anechoic chamber measurement, we would need things like the board files for the PCBs. If you have them, we would need the mechanical CAD for the enclosures, and we would need some description of the cables, be that a .kbl export from a wiring database, or those cables could be defined with a data sheet, a wiring diagram. Often the path of the cables is defined in 3D CAD, generally not necessarily the cross section of the cables in 3D CAD. That's okay. We know how to fuse those disparate data sources.
All right. Last question. How long does it take to learn to use EMA3D?
So EMA3D is a very quick to learn tool. I would say in the first couple weeks, you can be productive. You will learn immediately how to do shielding effectiveness of an enclosure. You will learn how to do radiated emissions from a cable with the signal in that cable. So for the basics, first week, it'll be part of your EMA or your EMC workflow. In terms of mastering it, it can take a few months to become an expert to make a full device model. But certainly this is a product that's going to enable a young engineer to be able to do that in a short period of time. The goal is a brand new EMC engineer right out of university should be able to start using the tool with minimal manual reading, minimal training, maybe just one virtual course or live course. They should be able to learn the tool and get productive with full devices within the first few months.
All right, it is time to conclude this session. As a reminder, any questions we didn't get to be addressed via email, or if you have a question you didn't get to ask, please email us. You'll also be receiving an email with a link to a recording of this presentation as well as the slides. If you have any questions, like I said, feel free to reach out to us via our website, EMA3D.com, or our email. Thank you for your time and attention and have a great rest of your day.